Alright, so sound waves. This is something that you can't see with your eyes, but you can hear it with your ears. If you took a look at the speaker demo, you saw how a speaker vibrates in order to generate the sounds that they do. What I did with the speaker was I played sine waves. And we'll go through the online tone generators a little bit, play a few different sine waves. I mean, you've heard them through the speaker, but we'll take a look at that as well. Essentially, I'm going to play an animation here. Again, I'll post this online. I'm not quite sure if the animations still work on the more recent version of PowerPoint, which is why I'm putting it here. But the point I want you to see here is that this is how a longitudinal wave is generated. When the speaker goes back and forth, what it does is it squeezes the air, compresses it, and then pulls it back, stretches it out, decompresses it. And if it's moving back and forth successively, you're going to see this happen with the gas particles. Now, you can't really see these particles with your eyes. But what's interesting to note is if you look at this, this kind of looks like a helicopter view of ocean waves. So you can kind of see the wave nature there. And then the cool thing is if you just fixate your eyes on a single particle there, what you're going to notice is that each of these particles goes back and forth. There is no particle here that continuously moves to the right. Now, so the wave is moving to the right, but the medium is oscillating back and forth. And basically what we've done here is we've made what we call a longitudinal wave. So if I diagram that out just really quickly and take a look at that, and there are certain regions in that wave that you really want to pay attention to. If we took a snapshot of that animation that I showed you, when the speaker does this, it pushes the gas particles closer together. When the speaker pulls away, it stretches them out. So you get these alternating regions of stretched out particles, compressed particles, stretched out particles, compressed particles, and it just keeps alternating as long as the speaker is doing that. And this is what the snapshot of the longitudinal wave might look like. Maybe make them a little bit more compressed just so that you can see it a little bit more clearly on the screen. So, based on these different regions here, if we think about the pressure, the air pressure that exists at this region, this region, this region, this region, this region, this region, this is a region of relatively low pressure compared to what we're used to. This is a region of relatively high pressure that we're used to here. So what we have here is that the regions of this wave oscillate above and below 1 atmosphere, which is the pressure that is typically around us at sea level. So if we're doing a pressure graph here of the snapshot of a wave, since this is low pressure here, it's probably going to look like this. And then the pressure is going to go up and it's going to go down because the particles are spaced far apart there. It's going to go up again because they're closer together, and it's going to go down. The pressure is what's oscillating here. So now you can kind of see the wave-like nature of it when we represent it with a pressure graph. And basically, if we were thinking about the wavelength of the wave, this would be the wavelength of the wave. So what you saw is that sometimes the speaker goes back and forth, not so fast. Other times it's rapidly going back and fast. So you can generate different sound waves here. You can generate a low frequency or a high frequency. And we've corresponded these to pitch. This is going to be kind of like a more bass pitch. This is going to be a higher pitch. And with the online tone generator, you're able to generate whatever pitch that you want to. So let's open that up real quick. If you play, like, let's say something 440, again, I'm not sure if my speaker is going to pick it up, but let's, oh my God, what happened? I touched something. It's back. Oh no, we're doing a frequency sweep here. Let's actually just go to the sweep generator. I'm going to hit 440. 440, because this will allow me to do that. Play the sine wave. We'll play it. That's actually, you know, a musical note, and it's got a specific tone to it. Maybe make the volume, it's about as high as it's going to go for me. If we want to increase the frequency, let's double it to 880. That's actually still the same note, but it's a higher pitch. Definitely detectable. If we go up to something like 2000, listening to that pitch, much louder. And then what we can do is this. We can go from a frequency sweep. What we'll do is we'll scan the entire range of sounds that you're able to hear. And you can do this on your computer at home because you can literally find out when your hearing stops. If you're a healthy teenager, you should probably go to about 18,000 hertz. However, if you've done a lot of damage to your ears over the course of time, you might have accelerated some of that. I think my hearing kind of fades out at around 15,000 hertz, but basically humans are able to hear anywhere from about 20 to 20,000 hertz. So when we do this frequency sweep here, and you can set how long you want it to take, but it's not going to take very long. It just keeps getting higher and higher and higher. Some people get really annoyed by this sound. I'm not one of those people. I can't hear anything anymore. Maybe you can. But you can literally find out where you can, what the highest frequency that you can still detect is. If you've got a dog in the room, you're probably going to drive him or her nuts. But what we want to also take a look at is not just frequency, but also wavelength and how it all relates to each other here. So one thing that we got to be aware of here is that our sound waves, they come at low frequencies, they come at high frequencies, all sorts of pitches. However, one thing holds true here. They both travel at the same speed, regardless of how they're generated. And it actually takes time for sound to reach your ears here. So if you got a speaker here and it's playing noise, what it's going to do is it's going to send out a sound wave. And you're way over here. That's going to take time for it to reach you. And it turns out that sound does travel pretty fast. In air, typically, it's 343 meters per second at room temperature. What ends up happening is that with different media, different temperatures, you can get the speed of sound to go up, you can get it to go down. We'll talk a little bit more about that at another time here. But basically, our wave speed equation is velocity equals frequency times wavelength. So, if we know the frequency and we know the wave speed, we should know the wavelength. Just looking at these two representations here, you can already see that this is a long wavelength, and this would be a short wavelength. So when you have high frequencies, you have short wavelengths. When you have low frequencies, you have long wavelengths. And basically, you're going to see that regardless of what your frequency of the wave is, you're going to get a corresponding wavelength, so that if you're at room temperature, the velocity will be 343 meters per second.